Hi there, thanks for stopping by for another episode of Mr. Ed Codes. And in this episode, I wanted to look at movement. How do we get things to move in coding? It's a huge problem. Not a huge problem, but it has a huge volume of answers. So there's lots of ways that you can approach the problem of moving an object around the screen. One of the most basic, and when I go through this example here, I'm going to try to relate what I'm talking about in terms of what people are used to from like 30 or 40 years ago. So if you're an old coder like I am, if you coded back when you were in middle school or high school, and then maybe you got away from it, and now you're starting to get back into it again. Learning what the new tools are and the code that they take over that you used to have to program yourself, that's going to be a little bit tricky. So I'm going to approach this example from trying to explain it in those terms. What are the things that we used to code back in the 80s, and how does that translate to what we're doing now in a modern programming language like Java, where we're using processing, p5.js, to make the code that's going to do a lot of the stuff that we used to do on our own. In this example here, I'm using something called Perlin Noise. But if you coded back in the 80s, just as a hobby, you probably used something like Brownian motion. And I'm going to pull up an example of that here. If you go to the p5.js website, there's a page called examples. In that, there's a section called, I think it's right here, simulate. Down in there a little ways is an example called Brownian motion. And if you click on that, it'll show you an example of that. And it'll give you the code. And it's pretty much what you're used to seeing. You've got an X and a Y. You've got a random value that tells it which direction to move in, and then you move in that direction and then you repeat those steps. The results of that movement are very random, and you can't really count on what it's going to do. It may stay in an area for a really long time and then venture away from it, like way far away, and then hang around there or go back. You just never can count on it. So in terms of being able to use this to actually get something to move around, it's not very effective. There are better ways of doing that. Another way that you could do it is Levy flight. I think it's a Peter or Paul Levy. It's the same as Brownian motion, but every once in a while you're going to take a huge step, and that gets you out of that location problem with regular Brownian motion, but it doesn't solve the problem of it looking robotic or too random. So to solve that problem, we use something called Perlin Noise, and this is pretty advanced. Perlin Noise it's something that was created in the 80s to help cope with the problem of this rigid randomness. What's rigid randomness? Well, they're random numbers that aren't related to one another. So you can be on one side of the range of random numbers, and then the next frame be on the other side of that random range, and that creates this kind of jumping flickering. So to avoid that, we want random numbers that will kind of move one way and then maybe move the other way, so there's no real harsh jumps. So that's basically what Perlin Noise does. So there's a function in p5.js that does that. We're going to give it some parameters. It's going to return a value between 0 and 1. And then we can just scale up that 0 to 1 value that it gives us to create our noise. In this example, I have an array of objects, and I have a function that basically does most of the work here. And you'll recognize parts of it because it comes from the example page. So let's go back there. Let's scroll down to the interaction part, and you'll see follow 1, 2, and 3, these examples here. Follow 1 is the easiest to understand. You can see it's pretty simple. The code itself is pretty basic. This is going to do the rotating and pretty much the following. This is going to figure out which direction we need to go, but we're not going to use the mouse. We're going to use something else instead. If you extend that process, you can get something like this. And then if you go even further, follow 3 will be a chain of those objects, just like this. We're going to use the first example, follow 1, because it's the simplest to understand. It has the easiest parts. So what I'm going to do is I'm going to take most of this, even these global variables here, they're going to go into the function when we instantiate it, and then we're going to update the object with this stuff here, modified substantially, and then we're going to perform the actual printing or drawing this object and rotating and doing that right here. So this is all pretty much going to go in its own function. So that's where we're starting at. I was going to type all this out with you and then you guys could follow along, but I think it'd be okay if I just went down line for line and explained what was happening and maybe get into the details of how this relates to traditional coding that we're used to back in the 80s, if you're that old. If you're younger and you're just learning, then maybe this will help you work it out in terms of X and Y, because we're going to be dealing with vectors, and it's a little bit different. And I'll explain that once we get down there. But to start, let's work with our global variables. I've got a variable here called mover. It's holding an array of objects. The size of that array is this population value here. That's all of our global variables. When we go down to setup, we're just going to create a loop that's going to loop through that population number, so 12 times. We're going to give that value to I, and then when we instantiate a new element in this array, we're going to pass I into the parameters of that instantiation. So our function, let me see, down here, when we first make this object, these variables are being created and assigned, and we're passing I into this instantiation part because we need to use that value in order to change a variable a little bit, and I'll explain that here, but that's what's happening here and that's why we've got that in there. So once we've instantiated our object and we've given it the parameter that it needs, we're going to go to draw. Just copy that loop, and instead of pushing into the array a new instance, we're going to go through the array. We have to tell it the index value here, and then we're going to use the dot syntax, and we're going to call a method in that function, and it's called update. We're going to activate that and perform those operations. So down in the function we have this method called update. Update isn't getting any parameters passed into it, so we don't need anything here. Once we've updated these, it's going to show them, go through the entire list of the array, and then start over and do that again and again. So that's draw. So we're creating our function here called vector mover. We're passing into it this parameter I, and then we're going to use that down here when we declare these variables and assign them for the very first instance of this. We need a position for this object, and we're going to use a vector. So vectors are really cool if you're not familiar with them, and this is, maybe you're just trying to get familiar with them and you've had people explain things but didn't really make too much sense, or you know about them pretty well, and you're going to listen to what I say and it's probably going to confuse you and you're going to be like, that's the worst way to explain it. Whatever the case may be, if you've got a better way to explain it, leave it in the comments, because there's always going to be somebody out there that will understand something one way and they won't understand it the other way. So this is just my way of explaining it the way that I understood it, because it was confusing when I was first learning it. The old school way of dealing with a location is we use an X and we use a Y. And then if we're going to move that location, we add to it some variable, like we'll say velocity. So our equation is going to, or our programming line in BASIC is going to look like let x equal x plus v, right? That's just going to move the x. And if you move the y, then you're going to put let y equal y plus v. Well, you can see the problem there is x and y are moving using the same velocity. So you'd have to have a velocity for your x and a velocity for your y. So now those lines are going to look like let x equal x plus velocity x, and then the other one's going to look like let y equal y plus v y. So now you're keeping track of an x and a y, you're keeping track of a velocity x, a velocity y, and that was all well and good. But wouldn't it be neat if you could have some kind of keyword that would keep track of both of those for you? So you could have a keyword that would create a position, and you could use that same keyword that could create a velocity or an acceleration. Or, even better, you could look at an angle and then derive from that angle what the x and y should be in terms of like a value from -1 to 1, and when you add that to your position, it's going to give you a vector. So now you have a heading from an angle that you can get using this keyword, this create vector. It's really, really powerful that way. So think of it in terms of you have three things in one. The primary way that this object is constructed, this keyword, this constructor, the p5 vector is a constructor and has a bunch of methods associated with it. And you can use those methods on the constructor and it will perform that operation, whatever it is. So when we use create vector, we can get from it primarily a position. That's basically all you have is an x and y coordinate value. But you can use x and y coordinate values as velocities. So say the position -1 x and the position 0 y, if you add that value to a position, well, you've created a vector because now you're moving to the left 1 unit according to that minus that -1 and 0. Does that make sense? So you can have a position, you can use that value as a vector, and if you multiply that times anything, you can get kind of a magnitude. Or you can take large numbers, factor out a size, and normalize it. So those are some of the things that you can do with this p5 vector keyword. In this case, I'm creating a vector, I'm setting to the x part of that, let x equal the middle of the width, let y equal the middle of the height. Now I'm creating a velocity, and I want the x, whatever I'm adding or subtracting to x is going to be 0. Whatever I'm adding or subtracting to y is going to be 0. Now it's not adding or subtracting it to them, I have to perform that operation. But the value to use for whatever operation I'm going to perform is already there. So if I need to move to the left, that's represented in a negative value. If I need to move to the right, it's positive, up, negative, down, positive. Okay, so now that we've got vectors out of the way a little bit for now, we're dealing in Perlin Noise. This is the next complicated thing we're dealing with. Perlin Noise needs an offset. It's because you're dealing with a field of pretty much predetermined values, and you're moving through this field, and then that field is giving you whatever random value is there. So if you have a range of numbers in this field, you want to offset it a little bit so you get a different range of numbers. And if you do it slowly enough, you can get some neat things to happen. So the offset value is going to be the index number. So I, that's what number of the object I'm on in its population. So if it's the first one, that's 0. I want to add to it 1 because I want at least, I don't want to multiply times 0. I want the product to be a non-zero number. So I'm going to add 1 to it, put it inside parentheses because of order operations. I want it to get multiplied against 5. And that's a large number. I'll make that smaller later on and you'll see what will happen. But for now, I want a big range, a big distance between where each element in the array, where it's getting its map of noise numbers. I want it to be far away from one another. If they're close together, then they're all going to get sort of the same numbers, but they're going to be delayed slightly. And it creates this cool effect that I don't want yet, but I'll show you that later. So for now, we're going to multiply that times a big number, and that number is going to change relative to whatever the element of the array is. Our object is going to be looking in a direction and then moving that way. In order to do that, we need an angle. we're going to be moving around a center point by radians of pi. So to keep those radians, we're going to use an angle value. We want our object to move in the direction it's headed, so we need a speed for it. We're going to use this value, we're going to multiply it times its vector, and that's going to give it its speed. Or multiply it times its velocity vector, this number here. And that'll give us our speed. The size of our object, its scale, I guess you could think of it as its radius. It's not, but just think of it that way, is 20. The way that I draw my ladybugs, I hard code the points. They're not factored. So if I change this number, the dots aren't going to change with it. So it's going to make my ladybug look all messed up. So for now, this just has to stay at 20. I don't even really need this, but I put it in there in case you want to scale this object once you factor all of the different points. Once we've instantiated our object and it gets all of its starting variables where it needs to be, whatever, we need to perform the method. So I create a method in this function called this.update. So in the body, the draw of our program, I call that method here, and I give to it the element, whichever one we're on. So it knows which one we're on. So it's going to perform the operations for that particular one. So it's going to add to its noise offset, which is determined here. It's going to add to that value this tiny number here. And then it's going to plug that into the parameters for our noise function, and then that's going to be inside the map of the to get the angle. So let's explain that a little bit. Our angle is going to be a number from 0 to 2 times 2 pi. The reason why I do this is because Perlin noise gets returned in the center of the range, and occasionally you'll get outliers, but by and large most of the values are going to be returned in a cluster around the center of that range. So if you just have that range as being one time around the circle, if it's concentrated in the center of that part way around, then that's the direction that this object is going to move in most of the time. It's going to be biased in that direction. So to spread out that range, I'm just going to go around the object twice, or increase the range of twice around, so that the cluster of Perlin noise will at least make it once around the object, and then it has a pretty much even chance of going in any direction. Play with this value if you want to see more of what I'm talking about. You can change this to quarter pi or a fraction of pi, and it will definitely alter how this object moves. Maybe we'll do that here at the end of this episode. Speed is the same way. I'm mapping a noise here. I'm mapping the inverse. So on one side of the origin is a range of noise, and on the other side of the origin is a range of noise, and they're not reflections of one another. So you can think of this noise field as having a center to it, and that's our origin, and then there's random noise values that go off in all directions. So if I take the inverse of the noise from one noise function and put it into another, I'm not going to get the same values, and that's important. I don't want my speed to be tied to the angle, meaning if it's turned to the left, it's going slow. If it's turned to the right, it's going fast. That's not going to happen here. I'm getting a totally separate set of Perlin noise using the inverse. I'm not going to get the reflection of that noise. And then I'm going to map it to a number between 0 and 4. This will never be 0. This value here will never be 0. It'll always be a really small number, but I don't think it'll ever drop down to 0. If it does, it's only going to do that for a frame, and that's going to go off of it. So my object is never going to be stopped. It's always going to be moving. Well, I want there to be a time when it stops. In order to do that, I'm just going to use a condition. I'm going to say if you're going so slow, you might as well be stopped. So I'm just going to stop you. So I'm going to test to see if we've dropped below a certain speed, and if we have, I'm just going to stop you. And then if the noise for this dot speed gets above that, then it will move whatever that value is, but otherwise it's going to be 0. So once we figured out our speed and we have our angle, now we're ready to plug that into our position. So how do we do that? The first thing we want to do is get a vector, an x and a y, from a radian. So this dot angle contains a radian. That's a number between 0, because of up here, my range for that is between 0 and 2 pi times 2. So this angle could be any one of those radians. Well, that's just an angle. That's not an x or a y. But I can figure out the x and y using some formulas. Instead of doing that, I just let p5.js do it for me with this method here for the vector constructor. So p5 vector dot from angle, put that value in the parameters, and it's going to return a vector, an x and y. And it's going to be a number between -1 and 1 for the x and -1 and 1 for the y. And then we just multiply that times the speed to get our velocity. And then we add that velocity to the position. So you can't just put this vector plus that vector. You can't do that. Because we're dealing with x and y's for each one of those variables, you have to handle it specially. You have to perform an operation on the x, you have to perform an operation on the y, and sometimes those are done in a very specific order in a very specific way. So to keep track of all of that, you can use the method for the vector constructor called dot multiply. So you're taking your whatever vector you want to multiply, you're adding dot mult, and then inside the parameters you're putting the value you want to multiply it by, and it's going to return a vector with the multiplication applied. Same with add. So that's how you do the let x equals x plus 1. This is kind of how you're doing that. But you're performing it to both x and y at the same time, and you're using an x and y, like a vx and vy, to do it. Once we have our position, we're ready to check and see, did we go out of bounds? If we did, let's handle that. So I created a method in this function called this.bounds, and I'm passing into it our position for our object. So let's go down to that method. Inside our function vector move, we have this method called this.bounds. We passed into it the position. We're going to give it to the variables x and y, and we're going to use that inside the body of this method. And then it's just 4 conditional statements that check for your x left and right, your y up and down, and if we go off the screen, we're going to move the coordinate to the other side. So that's what this is doing. Let's go back up here to our update. After we've found our bounds condition, made whatever corrections we need to, we come back out of that, we're back up into update. Now we're going to go to another method in this function called this.segment, and we're going to pass to it the coordinates again, but we're also going to pass to it the angle, because we need to be able to move the head of this object around. We need this variable. So then we go down, we make a method again called this.segment, and this is where it's going to do all of its activity. So I know this looks scary. This is all the dots and antenna and what have you, so you don't even really need that. What we do need is this part right here. That's going to create our bug, so its body and its head basically. So we're going to put all those changes inside a push and pop so that they happen just to this object and not to anything else. We're going to translate to the x and y position that we passed into the parameters of this function. So now our origin 0, 0, the program is going to keep track. It's going to know whatever, when I type a 0, what I really mean is whatever this canvas value is. When I type a 0 in the y position, it knows what that is. And then if I move away from that, it's going to do the math to figure it out. When I create this object, I'm not using an ellipse, I'm using a point. So it doesn't have a fill, it's just the stroke. And I'm setting that stroke to what would basically be the radius of this object. Because it doesn't have a stroke, if I want to outline this object, I have to put down one larger object with the outline color, and then put another object on top of it, and then the overlap will be the outline. So that's what I'm doing here. I'm placing a larger object that's black, I'm making a smaller point that's red, dropping that down. So if I look at this, just this part right here, I would have a red circle with the black outline. Now we have to rotate. And we're also moving away from our origin. So our head is going to be on the body, the perimeter of this first circle. To do that, we have to move away from the center point, this origin. We have to move away from that distance, a radius of that body. And then we're at the location that's, what's the tangent to. Once we're tangent, if we want to move around that circle, we have to rotate. We have to rotate from that position. So that's what we're doing here. We're taking the A that was passed into the method up there. We're putting that value into, where did it go? Oh, right here. We're putting it into the rotate, and it's going to perform that operation. It's going to rotate the object. Now we want to draw all the other stuff. So this is the head. This is going to make the head object. So it's a smaller point, about half the size or less, and it's black and just hangs off the body. And then as I rotate, that head is going to look like it's moving around that first circle that we made. So I'm going to make, let me see, what's these? Oh, the spots. These are the spots on the back. One thing to remember when you're kind of dropping points using a translated origin, we're using radians, so this object starts out at 0 radians. That's going to point it, I think, to the right. So X is now on the Y axis and Y is on the X axis relative to the canvas. So if we're dropping points relative to our canvas X and Y, it's not going to look right. It's going to be flipped because we're not looking at that X and Y. We're looking at the X and Y as it's been rotated 45 degrees to the right. That makes your X Y's and your Y's X's. They're still in the XY locations here, but if you're going to adjust the value and think you're adjusting it along the x-axis, you're going to actually be adjusting it along the y-axis. So just remember that, and it will become apparent once you realize that's not going down where I want it to, and this is why. So I'm making dots, symmetrical dots, you know, like a ladybug looks. If you need to know what that is, I just looked up a picture, I googled one, and I was like, okay, it has some dots that look kind of like this, and I just dropped them down. So it's not very scientific. It just generally looks like a ladybug. Then I put a line here that splits the wings, so I'm going from the head, where the head is at, this coordinate, to so far away from the head, down the object to its tail. So this is the tail coordinate, this is the head coordinate. I'm making a narrow stroke here because I want to draw some antennae. Is that a plural for antenna? So the origin of our head again, and we're just going to move up from there so far, and then we're going to move off to the left or right so far. So that's what this does. And we're going to do that again, except for if we used a positive number for the y here, we're going to use a negative for it here. And that's going to give us the reflection. So there's two antennae. Then the very last thing is, I think they have like white dots on their neck. So that's what this is going to do right here. So that produces the white dots. So here's the entire program, and here it is working. So I said I was going to show you some things that are pretty cool. The first thing is, let's reduce this to quarter pi, and we're not going to take a multiple of it. So just a plain quarter pi, and let's see what happens. You see how they're all heading in the same direction? The Perlin noise gets stacked up in the middle of quarter pi, so it's clustered around the middle of quarter pi. If I take this and put 2 pi, so that's a full circle, 2 pi, it should be okay, we would think, right? Well, no, even though every once in a while it might head backwards to the right, it's going to overwhelmingly be toward the left, because that's where the Perlin noise is clustered, in the center of that group of radians. So if we just multiply this times 2, now we're getting a cluster that's on one side and on the other. It's actually on all four sides. It's spread around the entire circumference of this object, so we get this more random and unbiased movement. Okay, the one more thing I wanted to show you before you go here is if you change this value here, it's a pretty large number now, but let's make it a small number and see what happens. So if we make this number smaller, what's going on? Why is it acting so weird? Well, the distance between the noise, each object is in that noise field in a certain position, and the further away that they are from one another, the more random their numbers are going to seem relative to one another. If you make them closer to one another in that noise field, in other words, if their offset is really close together, they're going to share a lot of the same values. In fact, it's going to be offset. That's where it comes from. That's offset value. That's how these numbers get to be relational, and how you can get undulating landscapes and water waves and all kinds of neat movement because of the relationship of these values. But you have to move them further apart if you don't want them to do this. But that is a pretty cool effect. If you had enemies in a video game, like enemy rocket ships that were flying around and attacking you, this would be a way for them to fly in formation. Kind of a neat way to get them to fly in formation. If you have a caterpillar object, this would be a way that you could affect a caterpillar's movements. Pretty cool. So let's set this back and see what happens. Set it back to where it was. Now they're further apart in that noise field. So their random numbers are less relational. Or there's more of a gap. You've passed through more of the noise. So much of the noise that it no longer looks relational. I hope you've learned something from this example here. I've learned a lot from doing this. When I was able to make this for the first time, I was like, yes, I finally understand vectors. I finally get it. I mean, I kind of got it. But relating it to what I used to know, that was the missing element. I mean, I understood what was going on in terms of JavaScript. But I wanted to see when I did this back 30 years ago, how is that being done now? So that was the missing link for me. And once I finally filled in that gap, it crystallized. So that's kind of my attempt here, is to help people maybe my age, or if you're just starting and this is kind of a tough concept, but you know about X and Y and X plus velocity X. If you know that kind of stuff, maybe this has helped you. If it has, let me know. I'd love to hear that. Leave a comment if you have any questions, or if you want to know anything else, if you have requests, let me know. And I guess that's it for this video. I really appreciate you watching. If you have this long, give me a thumbs up. And if you'd like more like this, hit subscribe, hit the bell to be notified. And until next time, as always, take care.